Hey everyone, in today's video we're going to talk about speed and how it's different from velocity. We'll also learn a few symbols that will appear next to some of the variables we'll see in physics this year, and we'll understand what to do when we see those symbols. So the first thing I want to talk about is how we calculate the speed of an object. There are three things that are related here: distance, time, and speed. Now you may already know what these three words mean from your everyday usage, but they have definitions that are specific to science as well. Of particular note is the definition of speed. Speed is defined as the rate at which an object travels some total amount of distance over some period of time. So it's the distance divided by the time. That's actually how we're going to end up calculating speed. Notice that the unit is actually a combination of the units of distance and time as well. Distance is measured in meters, time is measured in seconds, and so speed, being a combination of the two, has a unit that is a combination of those two units. Meters per second is just meters divided by second. So here's the formula that we call the speed equation. It says that speed equals distance divided by time. We're going to use this formula as one of our first tools of the year to understand how to solve physics problems. Now in this sample physics problem, I'm going to not only highlight what information is being provided to me and is being asked for, I'm also going to show you how you would normally get full credit on solving a physics problem with all the steps that are involved. It's not just your final answer that we want, it's all of the steps along the way that show that your work leads to your correct answer. So, the sample physics problem goes: a softball pitcher throws a pitch to a batter who is 13 meters away. The batter hits the ball 0.52 seconds after the ball was thrown. What was the speed of the ball? So the first thing I notice is that I'm being given a measurement of distance, which is the 13 meters away. I'm also being given a time measurement, which is the 0.52 seconds, and I'm being asked for the speed of the ball. You want to look in physics problems for the question words like what or where or how much or when, and then look for a measurement term that's close to it, because if they're in the same sentence, you'll probably guess, okay, that's the thing I need to solve for. So in this case, we need to solve for speed. So here's all of the work that you would need to show to get full credit. First thing you have to do is list your knowns and your unknowns. So I'm listing D for distance, T for time, S for speed. I know what some of these things are, and I'm not going to know one of them. That'll be the one I solve for. The distance that the ball traveled was 13 meters, the time it took to travel was 0.52 seconds, and the speed is unknown to us at this time. So I just put in question marks, but you could leave it blank or draw a squirrel or whatever you want next to the variable that is currently unknown. The next point that I would get if this was a 4-point question was for writing my equation. Now, eventually in the year in physics, you're going to have several equations to choose from, but right now it's pretty easy to see that this is the right one to use because it's on the page and it has all the same things as the variables that were given in the problem. Eventually it'll be harder to pick. So speed equals distance over time. I've been given distance and I've been given time, so the next step is to fill in the blanks, to plug in numbers, as math teachers sometimes say. So I'll plug in the distance as 13 meters, and I'll plug in the time as 0.52 seconds. Next, I would pull out my calculator, I would type in 13 divided by 0.2, and I would get a number of 25. The last thing you need to do before you circle your answer, though, is make sure that you have the correct unit of measurement on the end of your number. We just calculated a speed, so the unit should be meters per second. If you didn't have that memorized, it's okay, because you'll notice that I already can see what the unit should be based on the calculation I just did. In this case, I had 13 meters divided by 0.52 seconds. So if I'm thinking about this, I can probably figure out that meters divided by seconds is going to give me meters per second. So it's kind of two ways to figure out what your unit should be. Last thing is to circle your answer, and that just makes it easier for the teacher to see where your answers are. So now that we've seen an equation that relates to speed, which is based on distance and time, I want to start to talk about velocity, which is based on displacement and time. Here's an animation of a ladybug walking across the screen, and there's two paths being highlighted. The blue path is the actual traveled path of the ladybug. It shows all the steps that the ladybug took. And then the red arrow is showing the displacement of the ladybug. Now that's clearly different from distance. It seems to be suggesting that displacement is a line connecting your starting point and wherever you are, and that's kind of close to the definition, which we'll talk about on the next slide. So here's all of our old definitions and the old equation, and now we're going to learn some new definitions and a new equation. Down below there's a new concept called displacement. the symbol for displacement is x in order to differentiate it from distance, which is d. D was already used up, so we had to choose a different letter. And the definition for displacement is this. It's the difference between the start point and the end point of an object's travel. So if you did a bunch of winding steps on your way to school, you would only need to think about, for displacement, where did you start and where did you end? How far is your house from the school? That's the only thing that would matter. So sometimes this is called, in the old world, people would say this is as the crow flies. You could ask, how far do I need to drive to get to the local park? Or you could ask, how far away is the park as the crow flies? And that would be displacement, just a straight line path from one to the next. So the unit is still meters because this is still something that's describing a length of space. And time is going to be relevant to calculating velocity, which is another new concept for us now. But velocity is only a little bit different from speed because it uses displacement in its calculation instead of using distance. You may have heard the word velocity before, and usually it's said in a way where it means the same thing as speed. For example, a car could have a really high speed and it could have a really high velocity, and you might think those are interchangeable words. But in physics, they mean physically different things. Speed, above, is the rate at which an object travels some total amount of distance over some period of time. But now read the velocity definition down below. It's the average rate at which an object displaces itself over some period of time. So we're still talking about over time, but now the thing that is over time has switched out. Instead of distance, it's displacement. So here's the formula to calculate the velocity of an object. Velocity is basically just what is the rate at which you are getting from your beginning point to your destination. How efficient are you at getting there? If this ladybug had its speed calculated and then separately had its velocity calculated, they would be two different numbers because you'd plug in either the blue path, which is longer, or the red path, which is shorter. So clearly speed and velocity are different equations from one another. So let's practice with this new equation now that we've learned it. Here's our sample physics problem number 2 for today. The boy in the diagram rides his bike from the local park to his friend's house, and then bikes with his friend to the nearby woods to catch Pokemon. Sounds fun. It takes him 14 minutes to complete this journey. What was his average velocity? So like we did in the last problem, we're going to first try to identify what sort of information we are being given in the problem before we start doing out all these steps. I'm noticing that there's a measurement of time. It took the boy 14 minutes to complete his journey. And it's asking what will be his average velocity. So that's what we're going to have to solve for. Usually there's at least 3 things to think about in every physics problem. So we've got time, we've got velocity, maybe displacement is in here somewhere, or distance, but I don't see any other numbers. So where are they? Well, the diagram will sometimes provide information for you that isn't in the text of the problem. So I see a 4-mile distance, I see a 3-mile distance, and I see a 5-mile distance. In this problem, they're miles as opposed to meters because a meter's not very far, and it wouldn't take you 14 minutes to get 3 or 4 or 5 meters around places. So those are miles. So what are we going to use? Well, we're going to have to use the 5-mile distance that directly connects the point A to point C, the beginning of the journey to the end of the journey, because that's how we define displacement. So the boy's displacement is 5 miles, whereas his distance would have been 7 miles, because that's 4 plus 3. Remember, distance is your total path, and then displacement is just a straight line between your start point and your end point. So those are different measurements. So now we're ready to show all of our work and hopefully get an answer here. First thing I'm going to do is write down my list of knowns and unknowns. So that's x, t, and v. The displacement of the boy was 5 miles. The time that the boy spent traveling that whole displacement was 14 minutes. And the velocity is unknown to us. Next step, we're going to write down the formula that we're going to use in this case. It's pretty easy today to figure out which one it is because, again, we don't have that many formulas to work with at this time. So it's going to be this one, velocity equals x over t. So now let's plug in our numbers. The displacement of the boy was 5 miles, and the time that the boy spent traveling was 14 minutes. So now let's take out our calculators, let's type in 5 divided by 14, and we end up getting a number of 0.36, and our unit should just be whatever the units were that just went into this calculation. So if we were looking at how many miles per minute, that should be our unit right now, miles per minute. Now that isn't in base units. We don't use miles in the metric system, and minutes usually would be converted into seconds. We're not going to worry about that for now, for today, because we're just learning how to use these formulas. So that's how to use the velocity equation, which again is just a little bit more complicated than the speed equation because it uses displacement instead of distance. Now that you've learned those, we're going to learn a bit more about how to use these equations in the easiest way possible, because some problems will get harder than the ones we just saw. So on the left is the speed equation, and I'd like you to imagine taking that equation and then manipulating it somehow so that we can convert it into another form, make it look different. Using algebra, we could multiply both sides of this equation by the letter t. After we simplify that, it could come out looking like this. This is another correct version of the speed equation, and it goes distance equals speed times time. You can use this version of the speed equation to calculate how far something has traveled, whereas the first version of the equation could only tell you how fast the object was traveling. So that's an additional tool that you can now use in order to solve different kinds of problems. There's even a third version of this equation that you can use. If you take that top version and then you divide both sides by speed, simplifying, you will get this. Time equals distance divided by speed. This is another third correct way to use the speed equation, except this one calculates the time that it takes for something to happen when an object is traveling. This is also true for the velocity equation. There are going to be 6 equations in total on this page by the time we're done here. So look at the velocity equation and imagine now that using algebra, we multiply both sides of the equation by t. Simplifying, that would get us to something that looks like this. X equals v times t. Similar to the previous equation, this is an equation that can tell you the displacement of an object rather than telling you its velocity. So this would be useful in a situation where you're told velocity and time, but not displacement. And in fact, that's going to be the use for all 6 of these equations, is they're all good for different amounts of materials being given to you in different combinations. So the last one I'll show you is if we take that top version of the velocity equation and we divide both sides by the letter v, and then simplify, you'll end up getting something that looks like this. Time equals displacement divided by velocity. So this is great because we have 6 equations, which means there are 6 possible tools we can use in order to solve physics problems. And the more tools you have, the better equipped you are, right? Well, the drawback, of course, is that now instead of having 2 equations in order to solve problems, we have 6. So that means we need to be really good at remembering all these formulas, and we have to pick every single time which one we're going to use, and that could get really tough. So luckily, we're going to be able to use something called a formula triangle, which is what these 2 things are right here. What is a formula triangle? Well, it's basically a cheat code for memorizing all the different versions of an equation. And for most of the 3 variable equations that we'll see this year, you could possibly use a formula triangle, which you could make yourself, or I might show you in class, or you could just Google what the formula triangle would be. So here's how you use a formula triangle. Step 1, cover up the variable that you want to solve for. And I mean literally cover it up so that you can't see it anymore using your thumb or your finger or your hand. And then step 2, once you've covered up the variable you want to solve for, is to do the operation that you see remaining. So what do I mean by this? Well, it's kind of hard to show on a screen, so what I've done for this presentation is I've got a little hand symbol here, and I'm going to click and drag it around and move it on top of various variables here, and we'll try to see if covering them up and then doing some kind of operation resembles the equations, because what we're really trying to do here is replicate these 6 equations anytime we want using just these 2 tools. So let's look at the first version of the speed equation that we were given. Speed equals distance over time. Let's see if this formula triangle can get us what we need. So let's cover up speed, because that's the one that equation solves for. So cover up speed with my hand, and what's left over is d and t. And it's important to note that the d is on top of the t. So that's, in math, having one variable above another variable means that you should divide the top one by the bottom one, kind of like a numerator and denominator. So speed apparently equals distance over time. We'll look back to the formula, speed equals distance over time. So that works. Let's try solving for a different variable in this triangle. Let's solve for distance. If I cover up distance, let's look at what's left. Speed and time. And they're right next to each other. In algebra, when you have 2 variables like x and y or a and b, and they're right next to each other with no symbol in between, that means you should multiply them together. So apparently, according to this formula triangle, d equals s times t. Well, let's look back up to the second version of this formula that we saw, and in fact it says d equals speed times time. So I'm not going to go through all of these because that would take a while, but you can cover up any one of these variables And as long as the letters are in the right place in the triangle, you will always be able to get exactly the right version of a formula that you want for the test that you're taking, or for the homework assignment you're completing, or for the classwork you're doing, or just for the physics that you're doing at home for fun because you're passionate about learning science. Now, in the real world, would a scientist or engineer or someone who's really experienced with physics, would they use one of these formula triangles when they're doing a problem? Probably not. They would probably just remember the original version of the equation, and then they would use math or algebra to rearrange the formula into whatever version they need. But because we're new at this, and for the time being, you can feel free to use these formula triangles as your legal cheat code for the time being. So now that we've learned all about formula triangles, we are ready for our final topic of the day, and here it comes. There are things in physics problems that you'll occasionally see that might look a little weird at first, and they're called subscripts. A subscript is the opposite of a superscript, which is like when you're doing an exponent like x squared or x cubed. That top number, that's a superscript. A subscript is the opposite. It's on the bottom. So an example of a subscript in physics that you'll see is a lowercase letter I or an O or zero. And those words mean initial or original or beginning. And anytime those are attached to a letter, like in this case V for velocity, those mean you should pay special attention to the beginning of a situation. Sometimes objects will speed up or slow down, and they might have many different velocities throughout a physics problem. So you can't just say the velocity is this. Instead, you might say the initial velocity was this, and then you might say later that the final velocity was this. So here's my example of how these subscripts will work. If you had a runner who was running a race and they had just started the race, they just launched off the starting line, they might be running at, let's say, 2 meters per second. So you could say the initial velocity or the original velocity of the runner is 2 meters per second. But now imagine that they speed up, and by the end of the race, at the final time in this situation, they've sped up to 8 meters per second, which is pretty darn fast. Well, the final velocity and the initial velocity are different from each other. So you would have to make sure you're using these subscripts like I and F, or maybe O and F. You can use either I or O for the initial or original. It really depends on which textbook you're reading or what website you're using, which one of those pops up. But for the end of a situation, definitely use F for final. So now you can recognize those subscripts and know what they mean. They mean either at the beginning or end of a situation. But there's two more you should know too that are kind of weirder. Whenever you see a little bar over a letter, in this case we're looking at V bar, that means that you're expected to take the average value. So an example would be if we wanted to know what the average velocity was of our runner who started at 2 and ended at 8 meters per second, then we would have to do a quick calculation to figure out what that average velocity was. Now this is a really important concept when it comes to velocities and distances, because whatever object in a race has the greatest velocity on average, that object is going to win the race every single time. So even though your average velocity might only be your velocity for like a second of the whole race, that number is still the most important one for determining who wins the race. So your average velocity you hope is very high if you're in a race. So in this case, I took the average of the two speeds, which was 2, which was the beginning speed, and 8, which was the final speed, and then I added them together and divided by 2. So 2 plus 8 divided by 2 equals 5. So I figured out that the average speed of this runner would be 5 meters per second. The last subscript symbol I want you to know is delta. There's an entire alphabet of letters called the Greek alphabet, which we sometimes use a few of those thrown in physics and in other science classes to tell you certain meanings. And one example of that is delta. And of course you have your alpha and beta and gamma and epsilon and omega and all kinds of other funky letters. But for today, we're just looking at what delta means. So when you see delta, this triangle symbol, in front of another letter, it means the amount of change in that thing. So delta V would mean how much change in velocity was there. So for our runner, who started at 2 meters per second and ended up at 8 meters per second, how much was the change? Well, the change was positive 6. To get that, for numbers that are harder to do with mental math, this is the pattern. The change in velocity is just the final velocity minus the initial velocity. So in this case, that was a final velocity of 8 minus an initial or original velocity of 2, and that gave me 6. So the runner's change in velocity throughout the whole race was 6 meters per second. So now that you've seen these subscript symbols, you should be ready to do a lot of the type of work that we're going to do in this physics class. And it's very fundamental and important that you understand things like speed and velocity and distance and displacement, and of course time, because these concepts are central to a lot of the units that we'll study this year in physics. So I hope this was helpful, and I'll see you in the next video. Actually, scratch that. One more thing to talk about. I almost forgot. In physics, we have a sign convention that says anytime an object is moving up or to the right, we consider its motion to be positive. Whenever an object is moving down or to the left, we consider its motion to be negative. Now, there's no particular reason why right is positive and left is negative, or up is positive and down is negative, other than we just need to keep in line with each other when we use numbers that are positive and negative. For example, if I say a car is moving at negative 7 meters per second, that would mean it's moving at 7 meters per second in the negative direction, or to the left. So if you ever deal with a physics problem where something is moving downward rather than upward, you should input its motion information as negative, because that will tell the computer or the physics problem or the teacher that you're dealing with that you're describing downward motion instead of upward motion. And the same thing is true of left or right. So keep that in mind. And now I'll see you in the next video. Good luck.